Hi, this is Will Murray with Educator.com, and we're talking about differential equations. Today we're going to talk about slope fields, which are also known as direction fields. Those two terms mean exactly the same thing. So if you're looking at slope fields, you're looking at direction fields. If you're looking at direction fields, it's exactly the same thing as a slope field. So let's see what that's all about. If the idea is that if you can manipulate a differential equation into this form right here, you want to have y prime equal to some function in terms of x and y. The idea is that if you can manipulate it into that form, then you can use that form to draw what's called a slope field. And like I said, that's the same as a direction field. The way you do that is you take different points x and y, and at each point x and y, so for example, you might plug in x equals 1 and y equals 1, what you can do is you can plug in those values of x and y into the function right here, the f of xy, and it'll spit out a slope for you. It'll spit out a y prime. And so what you would do is you would go over to the point 1, 1 here. So there's the point 1, 1. And you would draw a little mark indicating the slope at that point. So for example, if y prime was 2, that would tell you that at that point 1, 1, you're going to draw a little mark with a slope of 2. And the slope of 2 is uphill, fairly steeply uphill. So I would draw a little mark like that. And you would do that for each combination of x and y that you're willing to graph. So you plug in maybe another combination, maybe x equals 1, y equals 0, and suppose you get y prime equals -1. You get this by plugging them into this equation right here. And then what you would do is you would go over to the point 1, 0, and you would draw a little mark with slope -1. So I draw a little mark here with slope -1. And you do that for all different points here. You find little slopes for all the points, and then you gradually go through and you fill up a graph with different slopes at different points. And what you get is called a slope field or a direction field. So we're going to have some practice with that over the course of this lesson. You'll get the idea. In the long run, this is something that you want to do on a computer. You want to have a computer draw slope fields or direction fields for you. And then the way you use them is you kind of look at them and you can see some of the solution trajectories to the differential equations. So let me talk a little more about that. The solution trajectories, what will happen is you'll have a slope field which will show lots of different slopes like this, maybe something like this. So you'll have all these little slopes, and what you'll do is you kind of connect those slopes up and you connect them into solution trajectories. So let me draw some sample solution trajectories here. There's one right there. I'm sort of following the slopes. I'm drawing curves that are parallel to the slopes wherever they pass through them. So here's some solution trajectories to this differential equation. And if we had the actual functions for these curves, these functions would be solutions to the differential equation. So what we're finding is different solutions to the differential equations. One key point here is the solutions never cross each other. So you want to be careful when you're drawing these solution trajectories to understand that they shouldn't be crossing each other. They sort of locally, they're always parallel to each other, and then they might diverge or converge, but they never actually touch each other or cross each other. Another thing that's key to understand is that these different solution trajectories correspond to different values of the arbitrary constant in the general solution to the differential equation. So if you remember when we solved some of these differential equations, we get things like y is equal to c e to the x squared. Something like that might be our general solution to the differential equation. And that c was an arbitrary constant. So that's an arbitrary constant. We don't know, at least initially, what the value of that constant is. And so if you plug in different values of that constant, you would get different graphs. And those different graphs are these different solution trajectories. So each one of these red curves here is a solution to the differential equation. They just correspond to different values of the arbitrary constant in the general solution. And to figure out which solution trajectory you want, you use an initial condition, which is usually given to you as part of the package in the differential equation. So you'll have an initial value for x naught and y naught. And what that does is that gives you an initial point, x naught, y naught, somewhere on the graph, and that will tell you which of the solution trajectories is actually the solution that satisfies not just the differential equation, but also your initial condition. So if we had an x naught, y naught, if you have an initial condition, that lets you narrow it down from a whole family of curves to just a single solution trajectory. So that's kind of the geometric picture there. Algebraically, we've already seen this process where we get a general solution to a differential equation. It has an arbitrary constant in it, and then what we do is we take this point and we plug in to the general solution. So you plug in x equals x naught, y equals y naught into the general solution to find the value of c. So that's how the initial condition can be useful algebraically, is you plug it into the general solution and solve for the value of the arbitrary constant c. Geometrically, what you're doing is using that single initial point to differentiate between all these different solution trajectories and pick the single one that fits your initial condition. So I think that's enough theory. I want to jump into some examples, and let's see how we can draw these slope fields or direction fields in actual practice. So in our first example, we have to draw a direction field. Remember, that's the same as a slope field for the following differential equation. Y prime is equal to x plus 2y. So what I'm going to do is make a chart of combinations of x's and y's, and for each one of those, I'm going to plug them into the differential equation, and I'm going to figure out a slope corresponding to it, and then I'm going to try to plot all those on a set of axes. So I'm going to make a fairly big graph here. I'm going to use a pretty big scale, so I'm going to maybe make that 1, that's -1, that's -1, that's 1, so 1, -1, 1, -1, 2, 2, -2, -2. And the idea is that I'm going to plug different combinations of x's and y's into the differential equation here and figure out what the slope should be at those different points. So I'll start out easy. I'll start with x and y are 0 and 0. And if I plug in 0, 0, y prime, remember y prime is always x plus 2y. That's from the differential equation. So then I just get y prime is equal to 0. And so what that means in terms of the graph is I'm going to go to the point 0, 0, and I'm going to draw a little hash mark with slope 0. So there's my hash mark with slope 0. Let me go back and calculate a few more points here. If I have x equals 1, y equals 0, then x plus 2y will just be 1. If I have x equals 0, y equals 1, then y prime x plus 2y would be 2. And if they're both 1, then x plus 2y would be 1 plus 2 times 1, so 3. So let me plot those. So 1, 0 that's on the x-axis. I'm going to draw a little line with slope 1. And draw my line here a little bigger. Little line with slope 1. 0, 1's up here. Slope 2 is a little steeper. So I make that a bit steeper. That probably still isn't steep enough. Let me try and make that a little steeper there. There we go. And at 1, 1, we've got the point 3. So that's really, we've got the value 3. So that's really quite steep. I'll draw that almost vertical. So there's a point that's almost vertical there. Let me go ahead and fill in some more points here that I want to find some slopes for. I'm going to try to calculate some slopes at each of those points there, I think. So I'll calculate those as fast as I can. I see I've got -1, 0, and y prime is x plus 2y, so that's -1 there. -1, 1. X plus 2y would be +1 there. See, I've got -2, 0. X plus 2y is -2. Negative 2, 1 is x plus 2y. That would be 0. And negative 2, negative 1. I'll just go across on the southern axis there. Negative 2, negative 1 would be x plus 2y would be negative 2 minus 2, negative 4. Negative 1, negative 1 would be minus 3. 0, negative 1. X plus 2y would be minus 2. 1, negative 1. X plus 2y is negative 1. And 2, negative 1. X plus 2y is 0 again. And I see there's a couple more points there. 2, 0. X plus 2y would be 2. And 2, 1. X plus 2y would be 4. So let me go ahead and fill in all my slopes. So let's see, I've done up to here. Negative 1, 0. I see I have a slope of negative 1, so let me give me a slope negative 1 there. Negative 1, 1 gives me a slope of 1. So there's the point negative 1, 1, and I draw a line with slope 1, so that's going uphill. Negative 2, 0 gives me a slope of negative 2, so that one's fairly steeply downhill. Negative 2, 1 gives me a slope of 0, so that's a horizontal line there. Negative 2, negative 1 gives me a slope of negative 4, very steeply downhill. Negative 1, negative 1 gives me a slope of negative 3, still pretty steeply downhill. 0, negative 1 gives me a slope of negative 2. 1, negative 1 gives me a slope of negative 1, so it's not so steep anymore. And 2, negative 1 gives me a slope of 0, so that's horizontal. 2, 0 gives me a slope of 2, pretty steeply uphill now. And 2, 1 gives me a slope of 4, so very steeply uphill. So the idea is that you go through and kind of as many points as you're willing to fill in. You try to find the slope by plugging them all into this differential equation, and then you draw these little hash marks everywhere through there. So I'm going to stop there because it gets a little tedious after this. But in the long run, this is something that is done very effectively on a computer. We're just practicing a couple by hand so that you understand the process. You understand what the computer is doing when it generates these pictures. What I'm going to do in the next example is show you a computer-generated picture of this slope field. You'll see it looks like my slope field, but it's got a lot more points filled in. So let me just remind you what we did here. We took different values of x's and y's, and then we plugged each one into x plus 2y, and we found these slopes. We found these slopes for each combination of x and y, and then we found those points on the actual graph, and for each one of those points, I made a little hash mark with that slope. For example, negative 1, 1. That means x is negative 1 and y is 1. So that's that point right there is negative 1, 1. And when you plug negative 1, 1 in to the differential equation, that means x is negative 1, y is 1. So y prime for that particular point comes out to be negative 1 plus 2, which is 1. So that's why we go with slope 1. And that's how I got this this hash mark with slope 1 right there. And so what I just did was I did that for every single point here. I found a y prime and I drew a little hash mark at each place. So in the next example, we're going to come back and look at this same differential equation, and we're going to use this slope field. We're going to draw some solution trajectories, but instead of using my crude hand-drawn graph here, we're going to use one produced on a computer. So let's see how that one turns out. So in example 2, we're going to use the slope field for y prime plus x equals x plus 2y from example 1. That was the slope field we generated back in the previous example. If you haven't worked through that one, you really want to check that one out so that you understand this example. In the next slide, what I'm going to do is give you a computer-drawn slope field, so it will be a little bit easier for me to work with it. What we'll do with it is we'll draw some solution trajectories to the differential equation. We're going to check that this equation right here is the general solution to the differential equation. So we'll actually plug it into the differential equation, and we'll check and make sure that it works, that it's the general solution. And then we'll look back at our solution trajectories and try to understand which ones correspond to which values of that arbitrary constant. So that's that arbitrary constant right there. We'll try to figure out which solution trajectories correspond to which values of that arbitrary constant in the general solution. So let's take a look at the computer-drawn slope field for this differential equation. Here it is. And this is something we started to draw by hand, but I got tired after plotting, 15 or so points. And so that's why I pulled up the computer-drawn example. The differential equation we were using was y prime is equal to x plus 2y. And what we have to do here is look at this direction field. So this direction field, remember, it comes from example 1. That's how you figure out where this picture came from. Is if you haven't just watched example 1, go back and check out example 1, and you'll see that we learned how to generate this this direction field. What I'm going to do is draw some solution trajectories here, which really means I'm going to kind of go through and connect the dots, except that the curves I draw have to be parallel to these little slope marks everywhere I draw them. So I'm going to draw these solution trajectories in red here. I see that there's kind of a dividing line here. If I just follow those straight arrows right there, I get one solution trajectory. That's the easiest one to draw, and now I'm going to draw a few more by kind of connecting these things up in curves that are basically whenever I touch an arrow, I should be parallel to that arrow. So let me draw a few more of these. Whenever I go near an arrow, I need to be following the slope dictated by that arrow. So here they start out more gentle, but they still end up going uphill. And they all the ones above this line here seem to be ending up going uphill. The ones below the line, I have to kind of turn myself to make these work. If I follow these these arrows, I got to be parallel to the arrows every time I touch an arrow. Every time I touch an arrow, I have to be parallel to it. So I'm sort of forced to be constantly turning downhill if I start below the line here. So those are my solution trajectories. The point of these is that any one of these red curves would be a solution to this differential equation. Any one of these red curves, because they're obeying the slopes at every single point, that means that they're obeying the differential equation at every single point. So they're solutions to the differential equation. Every one of these red curves is a solution to that differential equation. Now, we were actually given a general solution to the differential equation. Let me write that again here. That was y is equal to negative 1/2 x. I'm just copying this off the previous slide. Negative 1/2 x minus 1/4 plus arbitrary constant e to the 2x. We were asked to confirm that that is a solution to this differential equation. So what I'm going to do is I'm going to plug that into the differential equation, and I'm just going to see if it works. So I need to calculate y prime. Y prime, the derivative of negative 1/2 x is negative 1/2. Negative 1/4 is a constant, so its derivative is just 0, so plus 0. And then c e to the 2x, the derivative of that is 2c e to the 2x. And I see I can simplify that. That's negative 1/2 plus 2c e to the 2x. And so that's y prime. Let me work out the right-hand side of the differential equation. The right-hand side is x plus 2y. Let me label that as RHS for right-hand side. So that's the right-hand side of the differential equation. I'm going to see if I get the same thing as I got for y prime. RHS is x plus 2y. Now that's x plus, and I'm going to plug in my y from up here. So 2 times negative 1/2 x minus 1/4 plus c e to the 2x. And let me just simplify that. X, now 2 times negative 1/2 x is minus x. 2 times negative 1/4 is minus 1/2. And then I guess I get plus 2c e to the negative 2x. And those x's cancel, and it just simplifies down to negative 1/2 plus 2c e to the 2x. And if you check back up here, that y prime and the x plus 2y, when we worked them out, those are equal to each other. So we have a solution to the differential equation. We have a solution to the differential equation. We have found the general solution to the differential equation. And I got that just by plugging it into the differential equation and checking. And then the last thing we were asked to do is identify which of the solution trajectories correspond to which values of c in the differential equation. So let me write the general solution to the differential equation one more time. Y equals negative 1/2 x minus 1/4 plus c e to the 2x. Now, let me plug in some different values of c here. If I plug in c equals 0, then I just get y is equal to negative 1/2 x minus 1/4. That's a line. That's just, it's in y equals mx plus b form. That's a line. And it's a line with negative 1/2 slope. And I see that right here in the middle of my graph. It's this line right here in the middle. So let me flag this solution trajectory. This line is the line corresponding to c equals 0. So that's the solution trajectory corresponding to c equals 0. Now, what if I have a c value that's not 0? If I have a c value that's positive, then what I get is y is equal to, well, that same equation for the line plus c e to the 2x, where that c e to the 2x is positive. So what I'm doing is I'm taking that line and I'm adding an exponential function to it, which means, remember, e to the 2x, let me do a little graph of e to the 2x. E to the 2x looks like this. So I'm taking that line and I'm adding an exponential function to it. That's going to give me these positive, exponentially curving upwards solution trajectories. So all of these solution trajectories correspond to positive values of the arbitrary constant in the general solution to the differential equation. Now, if c is less than 0, I'll get y is equal to a line plus c e to the 2x, but this time the c would be negative. So essentially, if I do negative e to the 2x, the graph of negative e to the 2x will be curving sharply downhill. So I'm taking that line and I'm adding on a term that's sharply downhill, and that's how you get these negatively curved solution trajectories down here below that line. So all of these solution trajectories down here correspond to negative values of the constant in the general solution to the differential equation. So I've done everything I was asked to do here. We're supposed to take the direction field. Remember, we figured out the direction field in example 1. So if this graph that I started out with all the little hash marks, if that's a total mystery to you, go back and look at example 1. You'll see where it comes from. Except that in example 1, we just did it by hand, and here I produced a nicer computer-generated one. Looking at this direction field, I was able to connect up the hash marks and draw solution trajectories. The whole idea of that was that wherever I drew a curve, it had to be parallel to these arrows at wherever it was near an arrow. So it couldn't cut through an arrow like that or like that. It's got to be parallel to these arrows wherever it sees an arrow. So no cutting the arrows, it's got to follow the arrows. So I started out by noticing that some of these arrows gave me a straight line in the middle, and then if I sort of connect the dots above the line, I get these solution trajectories curving upwards. Below the line, I get all these solution trajectories, not supposed to be more parallel to the arrow, that would have to curve down. And when the next thing I had to do there was to check the given general solution and make sure that that really was a solution to the differential equation. So in order to do that, I worked out y prime on one side and I worked out x plus 2y independently. So here's me working out y prime, took the derivative, and then I worked out x plus 2y, where for the y, I plugged in what our solution is. So I plugged that in for our solution, simplified it down, and lo and behold, it did check. I did get the same thing as we got up here for y prime. So though that's nice that those two things did check each other out. That shows that we do have a solution to the differential equation. But finally, the problem asked us to determine which values of the arbitrary constant corresponded to which solution trajectories. And I started easy by taking the constant equal to 0, which just simplified me down to something in y equals mx plus b form. So that was just y equals a line. And so that's this line right here at c equals 0, this line right in the middle. And then I checked if c is not 0, then what we're doing is we're either adding or subtracting an exponential function to our line. So here's my typical graph of an exponential function. It goes up or down depending on whether you're adding or subtracting. And so we're taking that line, and so these more complicated solutions will diverge from that line by either going uphill if c is greater than 0, or by going downhill if c is less than 0. So I figured out which kinds of values of the constant will correspond to which family of solution trajectories. So let's keep moving and try another one. In example 3, we're going to draw a direction field for the following differential equation. Y prime is equal to negative x over y. So I'm going to start by making a little chart here in which I'm going to list various combinations of x's and y's, and then I'm going to plug them into the differential equation, and I'm going to see what I get for y prime. And once I've got a good number of points stored up, I'm going to draw a graph of those and see if I can get a general idea of what the direction field would look like. So there's 1, there's negative 1, negative 1. Oh, that one was a little far out. Let me draw that a little closer. There's negative 1, and there's 1, 2, 2, and so on. So what I'm going to do is start with different combinations of x's and y's and try to plug them into the differential equation. I'll try 0 and 0 because that's always a good one to start with. Unfortunately, if I try to plug that into negative x over y, I get 0 over 0, which is undefined. So I really don't get anything useful there. I'll try x is 1 and y is 0. And then I get 1 over 0, well actually negative 1 over 0, which I think of that as being infinity. So I think of that as being infinite slope. I'll think of that as being a vertical line. So at 1, 0, I'm going to draw a vertical line here. Let me try 1, 1 and 0, 1. If I plug in 1, 1, I get negative x over y. Negative 1 over 1 is equal to negative 1. So the point 1, 1, draw a few more points here that I'm planning to fill in. The point 1, 1, I just figured out has slope of negative 1. So I draw a line with negative slope there. The point 0, 1, if I plug that into negative x over y, I get negative 0 over 1, which is 0. Let me do some more points there. Negative 1, 0 gives me 1 over 0, which is, I think of that as being infinity, so I think that's going to be another vertical line. Negative 1, 1 will give me 1 over 1. Plugging that in, that's going to give me 1. Negative 1, negative 1 will give me positive 1 again, because there's 3 negative signs there, so it's, negative 1, negative 1, let me write this out. There's so many negative signs, it's hard to keep track. Negative, negative 1 over negative 1. 3 negative signs will give me negative 1. negative 1, 0, negative 1 will give me 0 over negative 1 will give me a 0 again. 1, negative 1 will give me a positive 1. 2, 2 gives me negative 2 over 2 is negative 1. Actually, I didn't want to do 2, 2. I didn't want to go that far. I think I'm just going to do 2, 1, which gives me negative 2 over 1, which is negative 2 over 1 is negative 2. Negative 2, 1 gives me 2 over 1, which is positive 2. And negative 2, negative 1 gives me 2 over 1, which is, negative 2 over 1, because there are two negatives and then a third negative, is negative 2. And 2, negative 1 will give me 2 over 1, which is 2 again. So let me go ahead and try to fill in all of those slopes. 1, 0, I already filled in that one. 1, 1 gives me negative 1, filled in that one. So those are the ones I've filled in so far. 0, 1 gives me a slope of 0, so I'll draw a horizontal line there. Negative 1, 0 gives me an infinite slope, so I'll draw a vertical line there. Negative 1, 1 gives me a slope of 1, so there's negative 1, 1. And 0, negative 1 gives me a slope of 0. 1, negative 1 gives me a slope of 1. Looks like I forgot negative 1, which gives me a slope of negative 1. 2, 1 gives me a slope of negative 2, so that one's more steep. Negative 2, 1 gives me a slope of 2, so that one's more steep. Negative 2, negative 1 gives me a slope of negative 2. Steep line there. 2, negative 1 gives me a slope of 2. And you start to see a pattern emerging there. On the axes, on the horizontal axis, it's always vertical. On the vertical axis, it's always horizontal. And then we get these, what we're really getting is a circular pattern here. It's going to look like patterns of circles here. A circular slope field. So that's all we had to do for that one. Let me remind you about the individual steps there. I took different points, x's and y's, different points. I plugged them into the differential equation, negative x over y, and for each one I got a y prime. So as an example there, here's the point negative 1, 1. So I took that point negative 1, 1 and I plugged it in there and I got negative. Now x over y is negative 1 over 1. And so that turns out to 1. So I draw a little slope mark there. I draw a little line there which has slope of 1. And so that's how I got that little line right there. And then I just went through the different places all over the plane. For each place, I took an x and a y, my x and y coordinates, I plugged them in, and I got a slope, and then I drew a little hash mark with that slope. So I get this direction field. In the next example, we're going to use this direction field to try to draw some solution trajectories. We're also going to compare them with some actual solutions to this differential equation, and we'll see what kinds of solution trajectories correspond to different values of the constant. Now, I am going to use a computer-generated direction field in the next example, but it's just a computer-generated version of this same thing that we're drawing by hand here. So I want to stress here that the computer is not doing anything mysterious. It's just saving me time and drawing a slightly nicer graph than I could draw by hand. So let's go ahead and check that out. So in example 4, we're going to begin with the direction field that we drew for example 3 for the differential equation y prime is equal to negative x over y. In the next slide, I'm going to give you a computer-generated version of that direction field we had for example 3. So we'll work with that on the next slide. Here's what we're going to do with it. We're going to draw some solution trajectories for the differential equation. We're going to take this solution to the differential equation and check that it actually works. So the solution is x squared plus y squared is equal to a constant. And then we'll solve the differential equation subject to the initial condition y of -3 is equal to -4. So let's keep all this in mind. On the next slide, I have a computer-generated direction field for this differential equation, but it shouldn't be anything mysterious because it's something that we already started working out by hand in the previous example. So let's jump over and take a look at that. So in this slide, what I have here is a computer-generated direction field for the differential equation. Let me remind you what the differential equation was. It was y prime is equal to -x over y. And the idea is that we started drawing a direction field by hand in example 3. So if this sudden mess of arrows here looks completely foreign to you, what you want to do is go back and look at example 3, just a couple of slides back. It's where we started generating this direction field by hand, and I actually plotted points and I showed you where each one of these little arrows comes from. In this slide, I just wanted to have a prettier one and one that with more arrows so it's easier to figure out what's going on. So the first thing we had to do here is to draw some solution trajectories, and it's pretty clear that if you just connect up the arrows here, what you're getting is circular patterns. So let me draw some of these circles. The idea is whenever I'm tangent to an arrow here, it should be parallel. It should be parallel to the arrows that I'm touching. So that's what I mean by tangent. So what I'm getting is exactly circles, as long as I follow the slopes of the arrows all the way around. Make that one a little narrower. My circles aren't so good. This is why I have computers draw these things when I really need them to look right. So there's my circle. Let me draw one more. Hopefully it won't get too lopsided. The idea is that I'm staying parallel to the arrows everywhere I go around. So I never want to have one of my solution trajectories really crossing an arrow. I just want it to be parallel to an arrow, to the arrows all the way around. So those aren't bad solution trajectories, considering my inherent level of artistic skill, which is pretty darn low. So those are my solution trajectories to the differential equation. The second thing we had to do was take a prefab solution and check that it was really the general solution to the differential equation. So that was x squared plus y squared equals c. That was given to us on the previous slide. I want to check that that works in the differential equation. So that means I'm going to work out y prime here. Now, because I've got a y squared here and not just y by itself, I'm going to use implicit differentiation to take the derivative there. If you don't remember how to do implicit differentiation, either you're going to be reminded really quickly on this example, or if it's completely foreign to you, you might want to look at the Calculus 1 lectures here on Educator.com. We got a whole series of lectures on Calculus 1, and one of them covers implicit differentiation. So I'm going to take the derivative d by dx of both sides here. X squared plus y squared is equal to c. We'll take the derivative of both sides with respect to x here. Derivative of x squared is just 2x. The derivative of y squared is 2y times dy by dx. That's by the chain rule. And then the derivative of a constant is just 0. So that's implicit differentiation there. What I'm going to do now is solve for dy by dx. So I think I can cancel the 2's by dividing both sides by 2. So I just get x plus y dy by dx is equal to 0. Just divided both sides by 2. Y dy by dx, trying to solve for dy by dx, is equal to negative x. Move the x over to the other side. And so dy by dx is equal to negative x over y. Of course, dy by dx is the same as y prime, so I get y prime is equal to, whoops, I forgot my negative sign, negative x over y. And lo and behold, I see that it does satisfy this differential equation. So I've now checked that that is the general solution to this differential equation. So the last part of this example, the last task we had to do, was to solve the differential equation subject to the initial condition we were given in part C of the differential equation, in part C of the instructions. We were given y of -3 is equal to -4, which means we're going to plug in x equals -3 into the general solution, -3, and y is equal to -4, and we're going to see what value of the arbitrary constant we get. So if I plug those into, we had x squared plus y squared is equal to c, and so x equals -3, -3 squared plus y equals -4 squared is equal to c. I see that I'm going to get c is equal to 25, and so if I plug that back into the general solution, what I get is x squared plus y squared. Y squared is equal to 25. Now, that is an equation we can readily recognize as the equation of a circle of radius 5. Let me just show what that kind of represents here on the picture. The picture that corresponds to plotting an initial point. So it's about -3, -4. I see I've got my scale a little unrealistic here. It won't show -3, -4. So I'm going to try to estimate it, even though it would actually be a little farther out. I'm going to say that that's the point -3, -4. And what that means is we found which of these solution trajectories goes through that initial condition. So we've narrowed it down from a whole family of solutions to a particular solution that solves the initial condition. By the way, what you should be noticing here is that just by looking at the graph, we figured out that these solution trajectories were going to be circles. So we drew these circles, but that was before we ever saw the general solution. However, when we look at the general solution right here, x squared plus y squared equals c, I know that that is the equation of a circle, so that kind of confirms what I had already guessed from my graphical intuition. So this is going to be circles. It's just going to be different size circles depending on what the value of c is. And that definitely corresponds to our graphical intuition, where we have circles of different, each one of a different radius. Circles of varying radiuses. So circles of different, each one of a different radius there. So let me recap what we did here. The first thing we did was to take the graph of the slope field. Remember, that's the same as a direction field that we had figured out in example 3. So that's where this graph really came from, was from example 3. In example 3, we did it by hand. In this example, I kind of upgraded to a computer-drawn one. But you should now understand where the computer-drawn picture comes from. So it shouldn't be something mysterious coming out of the computer. You should just be saying, okay, yeah, we just used a computer to maybe draw something a little more complicated, a little quicker, and a little more accurate and pretty than what we could have drawn by hand. So we took this direction field that we had produced in example 3. We drew some solution trajectories, and the key part there was that I was going around and I was drawing these curves that kind of follow the arrows wherever they touch an arrow. So wherever they touch an arrow, they're supposed to be parallel, tangent. The arrows are supposed to be tangent vectors to these curves. So I can't sort of cut across arrows like that. That would be bad. Instead, I have to follow parallel to the arrows wherever I go. So I follow these arrows parallel wherever I go. So we drew those solution trajectories, and it turned out that we got circles. The next step there was to take this given general solution, x squared plus y squared equals c, and use it to check that it really is a solution to the differential equation. So in order to do that, I wanted to calculate y prime, and I had to do that by implicit differentiation, which is what I'm doing here. I'm doing implicit differentiation, which is something we learned how to do back in Calculus 1. So if that looked totally foreign there, then maybe check back at a lecture in the Calculus 1 lectures on implicit differentiation. So we took the implicit differentiation, we figured out, we solved for dy by dx, and we got dy dx, or y prime, is equal to negative x over y, which exactly is the differential equation that we started with. So that tells us that we do have the general solution to our differential equation. So that was the second task there. And at the same time, I kind of noticed that this equation we were given, x squared plus y squared equals c, that is the equation of a circle, and it just has a different size radius depending on what c is. So plugging in different values of c is why we have many different circles here. Each one corresponds to a different value of c. And then finally, for part C, we were given an initial condition here, and we used that to plug in an x and y and actually get to a specific value of c and narrow it down to a specific solution. So that kind of geometrically corresponds to starting at a particular point and saying, okay, that's going to narrow me down to a single solution trajectory instead of a whole family of solution trajectories. So in example 5, we're going to draw a direction field for the following autonomous differential equation. And let me mention this word autonomous. What that means is that there is no x in the right-hand side. It's just a function of y. So there's no x on the right-hand side, which really means we only need to look at the y values. So there are no x's here. No x's, which means we only look at the y's. Now, that's going to have very interesting consequences for us. What I want to do is maybe do a little algebra on that function on the right, and then we're going to try to graph that function before we actually draw our direction field. What I can see with this is that I could factor out a y, and I'll get y times y squared minus 3y plus 2. And that's y times, that would factor into y minus 1 times y minus 2. And the key point about that is that that would be 0 if y is equal to 0, or y is equal to 1, or y is equal to 2. Now I'm going to try to graph that function before I do my direction field. This is called phase plane analysis, and you'll see some more of it later on in your differential equations, but I just want to get you used to it now. What I'm going to do is I'm going to graph y prime versus y. This is the phase plane analysis. This is not the same as the direction field. I'll draw the direction field over here and try to make it very clear the distinction between the two. So the key thing here is in the direction field, your axes are labeled x and y. In the phase plane analysis, we're looking at y and y prime. And so I'm going to graph this function y cubed minus 3y squared plus 2y. What I know is that that has zeros when y is equal to 0 and y is equal to 1. I think I'm going to make this a little bigger. Give myself a little more space here. I'm not going to use the negative side so much, so I'm going to give myself more space on the positive side. So y is equal to 0, and y is equal to 1, and y is equal to 2. And I know it's a positive cubic function. I know the generic shape for cubic functions is it goes up and down and up again. So it's something like this. So what I just graphed there is y cubed minus 3y squared plus 2y. And I'm going to use that to inform my graph of y versus x. So what I've done here is I've looked at where y prime is positive or negative in terms of y, and I really only have to look in terms of y, and that's because there were no x's appearing on the right-hand side. What I notice here is that at y is equal to 0 or 1 or 2, y prime is equal to 0. Y prime is equal to 0 whenever y is equal to 0 or 1 or 2. Now over on the y versus x graph, the y is on the vertical coordinate. So there's y is equal to 0, there's 1, there's 2, and that means that wherever y is equal to one of those values, y prime is 0, so that means I have horizontal slopes there. So let me draw some horizontal slopes there. These are horizontal slopes. And I'm doing this at y is equal to 0, 1, and 2, and that's because those are the places where y prime is equal to 0. So those are my horizontal slopes. And now I want to kind of look in between those areas and between those cutoffs and see what kinds of values I'm going to get for y prime. So if I look down here where y is less than or equal to 0, I see that y prime is negative. Which means that whenever y over here on the right is less than or equal to 0, I'm going to see some negative slopes. So let me draw some negative slopes here. There's a negative slope. There's a negative slope. Now I don't really care what the x does because the x did not appear in the differential equation. So there's some more slightly negative slopes. Don't really care what the x does. That's why I'm not really paying attention to my x values here. When y is between, there's 0, there's 1, there's 2. This is y prime was equal to 0 at y is equal to 2. Now, when y is between 0 and 1, what I see here is that my y prime is positive. So I'm going to see some positive slopes, some positive slopes in between 0 and 1. So I go in between 0 and 1 here, and I'm going to draw some positive slopes. Draw some more gently positive slopes here because they're approaching 0. And some more gently positive slopes here because they're approaching 0 as well. And now when I look at y's between 1 and 2, so here y, remember y is on the horizontal axis over here, y is between 1 and 2, I see that y prime, the y cubed function, y prime is negative again. And so I'm going to draw some negative slopes here in between 1 and 2 on the y-axis. Some negative slopes. Some more gently negative slopes there. So some more gently negative slopes. Maybe I'll fill those in a bit. Fill in some more of these just so you get a better idea here. Steeply negative slopes, steeply negative slopes, steeply negative slopes. I'm going to show you a computer-generated picture of the same thing on the next page, but I think it's useful to draw one or two of these by hand in your life. And now, if I look at y greater than 2, y bigger than 2, I see that my y prime is positive again because this curve is above the horizontal axis. so it's positive. So over here on the y versus x, axes, I'm going to put some positive ones, positive slopes here. Positive slopes. And I see that as I go for bigger and bigger values of y, they're not leveling off, they're just getting steeper. So let me draw some steeper slopes here. And over in the negative range, they're getting steeper as well. So it's a little hard to make sense of all this, but if you go through, I see that I've got a couple horizontal lines that kind of can help me inform all the other solution trajectories. I've got these horizontal lines here, and then sort of in between these horizontal lines, on the regions below, everything seems to be sloping down. On the regions in between, I've got these solution trajectories that are kind of sloping gradually up towards 1, and then sloping gradually down towards 1. And then up above 2, everything just seems to be sloping steeply up towards infinity. So let me remind you how we figured everything out here. I'm going to show you a computer-drawn slope field for this differential equation on the next slide, but I don't want that to come as a revelation. I want you to understand where these slope fields come from. So what we did was, the first thing we noticed was this word autonomous keys us into the fact that there's no x's on the right-hand side. So there's only y's. It means we just have to look at the values of y, and we can sort of ignore the x's completely. So in order to really understand this, I factored it down. I factored out a y first, and then I factored that into y times y minus 1 times y minus 2. And then I was going to try to graph that, and I noticed that that's going to be 0 wherever y equals 0, y equals 1, or y equals 2. So when I graph that with y on my horizontal axis, I get these 3 zeros right here, 0, 1, and 2. And then I know I've got a cubic equation. Cubic equations, they all have that shape or that shape. And since this one has a positive leading coefficient, I'm going to draw my cubic equation in the positive direction like this. And then I can use this. Remember, this is not the slope field. This is not the graph of x versus y. This is y prime versus y. What I have over here is y versus x. So two different graphs of two different things, but I'm using this graph on the left to figure out how to draw the graph on the right. And so I look at this and I see when y is 0 or 1 or 2, then my y prime is 0. So whenever y is 0, 1, or 2, that's why I got these horizontal lines whenever y is equal to 0, y is equal to 1, or y is equal to 2. That's why I get slopes of 0 for those three values of y. And then I look in between those values, and I try to see whether this graph over on the left is negative or positive. So I see that it starts out negative, then it goes positive, then it goes negative, and then it goes positive again. And so when I look at my slopes here, I'm going to draw negative slopes down here, positive slopes down here, up here, negative slopes again, and finally positive slopes. And those come exactly from, I guess that comes from here, that tells me that, and that tells me that. All that information comes from the graph on the left about when the slopes are positive or negative. By the way, when I was drawing these solution trajectories, remember that these solution trajectories never cross each other. So I was pretty careful to draw these in such a way that even though they're asymptotic to each other, they'll get very, very close to each other, they never cross each other. So whenever you're drawing these solution trajectories, you want to make sure that your curves don't cross each other. If so, then you've really probably misread either the equation or the direction field. in some way. So we're going to keep going with this direction field on the next example. So you want to kind of make sure you understand where this direction field comes from before you move on to example 6. In example 6, I'm going to start you off with this direction field, or actually a computer-drawn version of this direction field, and we'll draw our solution trajectories, and then we'll start talking about limiting behavior of different solutions starting at different initial points. So stick around for that. So in example 6, we're going to start with the field that we had for the differential equation y prime is equal to y cubed plus 3y squared plus 2y. So we graphed this in example 5. If you haven't just watched example 5, what you want to do right now is go back and watch example 5, because that's where we generated the direction field, and we're going to use that direction field to solve example 6. So the first thing we're going to do is draw some solution trajectories. We actually saw some of those back in example 5. And then we're going to describe the limiting behavior as x goes to infinity for a bunch of different starting points. We're going to do 0, 1, and 1, negative 1, 2, 1 half, 3, 3 halves, and 2, 3. So we're going to look at each one of those starting points and see where the solution trajectories would end up if we started at each one of those initial points. So I'm going to jump ahead to the next slide where I've got the solution, the direction field all ready to go, a computer-drawn version. Alright, so this is the direction field for that differential equation. Let me remind you what that differential equation was. It was y prime is equal to y cubed minus 3y squared plus 2y. And we started with that equation back in example 5, and we generated this direction field. So this direction field should not be a mystery to you. You should be kind of nodding your head in recognition. If you're not, if you're looking at this and wondering where it came from, then just go back and watch example 5, and you'll see exactly where this comes from. So first thing we had to do was draw some solution trajectories, and we already got an idea of this in example 5. I'm just going to draw some curves that follow these arrows, and the idea when I draw these curves is wherever they're touching an arrow, they should be tangent, and meaning parallel to the arrows. So I guess I should have started by drawing those equilibrium solutions. Y equals 0, y equals 1. That's a little hard to see. Let me separate that from the black line a bit. And y equals 2. And then let me go ahead and fill in some more of these. So I have to follow the arrows wherever I touch them. They should be parallel to the arrows if I do my drawing right. So these are sloping uphill, but then they kind of level off. And also, if I do my drawing right, these curves will never touch each other. Remember, solution trajectories, they might be asymptotic to each other, but they never touch, and they certainly never cross each other. So if I draw good ones here, they'll never touch each other. They might be parallel, they might be asymptotic to each other, but once they'll get close to each other, but they'll never touch. And then I see that the ones up here are just curving steeply uphill. Remember, this slope field, this direction field with all the arrows is not supposed to be a mystery where this came from. I drew it on a computer, but that was only to save me time. This should be something you could generate by hand if you absolutely had to. Certainly you should understand what the computer did to draw this direction field. It's not supposed to be a mystery at all where these arrows are coming from. So those are my solution trajectories, and now I've got to look at these different initial points and describe where they're going to end up. So this first one, I'm starting at the point x equals 0, y equals 1. Let me find that. That's right here. X equals 0, y equals 1. And I see that that's just going to follow this straight line solution trajectory. So the limiting behavior there, the limit as x goes to infinity of that is just going to go to 1. Because it's just staying there at y equals 1. The limit of y of x, let me give myself a little more space in case you're having trouble seeing that at the edge of the screen there. The limit as x goes to infinity, of y of x each time is what we're going to figure that out. Is how we're going to figure that out. Now, y of 1 is equal to negative 1. That means we're starting at x is equal to 1 and y is equal to negative 1. So x equals 1 is here, y is negative 1 here. And so that looks like it's going to catch up with one of these solution trajectories that's just going down to negative infinity. So that's going nowhere but negative infinity. So the limiting behavior of that solution would be negative, let's see, make sure I have space here, negative infinity. Y is going to negative infinity. Now, y of 2 is equal to 1/2. That means I plug in x equals 2. Y is equal to 1/2, and we'll see what solution trajectory that one catches up with. 2 in the x direction, y is 1/2, so that looks like I'm starting right there. And if I pick up the arrow that's just going past me, looks like I'm going to asymptotically approach this solution trajectory at 1. So that one is going to approach 1. Again, it's going to approach 1. Now, the next one is y of 3 is equal to 3/2. So I'm going to find the point x equals 3, y is equal to 3/2. X equals 3. 3/2 is between 1 and 2, so it's going to pick up right there. So, looks like it's headed downhill, and then it's going to level off, and that one's also going to head towards 1. What we say here is that 1 is a stable solution, meaning that the other solutions are attracted towards 1. 1 is a stable equilibrium solution. By contrast here, 0, if you look at the solution trajectories around 0, they're going away from it, and so we say 0 is an unstable equilibrium. Same thing with the equilibrium solution at 2. All the other solutions are traveling away from it, so we say that that's an unstable equilibrium. So this is a stable equilibrium solution at 1, which is why the other solutions are trying to approach it. Now, the last one we have here is 2, 3. So start at x equals 2 and y is equal to 3. So here's x equal 2. Y is equal to 3 is up here. And I see that if I hop on the bus at that point, it's going to be trending straight up, very, very steeply up, up to negative, no, not negative infinity, positive infinity. And so that solution is rapidly going to diverge up to positive infinity. So let me recap what's going on here. We started out with this graph of the slope field, which is the same as a direction field. That's for this differential equation, and we actually created this direction field back in example 5. So I put up a nice computer-generated graph here in example 6, but it's not supposed to be a mystery where that came from. It's just a matter of going through and doing the phase plane analysis. So maybe go back and look at example 5 if you need to, and then this graph is all supposed to make sense. What we did with this example in example 6 was we colored in some solution trajectories. That's what I did in red here. And I did that just by following, let me do a couple more in green. I did that by following the arrows wherever I saw them. So I'm just kind of, I'm trying to keep my solutions always tangent to the arrows. And I'm also remembering that these solution trajectories never cross each other. So I have to be careful that I don't draw them crossing each other. When they start to get close, then they end up becoming almost parallel to each other. They get asymptotically close to each other, but they never cross each other, and they never actually touch each other. So I just filled in, I connected in these red curves here, I connected the arrows into some solution trajectories. And then I was given a sequence of initial conditions here. That's what all these y values are. And those correspond to starting points. And the question is, if we start at those different points, where are we going to end up? And if we start at those points and follow the solution trajectories, what kind of y values are we going to approach in the long run? As x gets very big, what y values will we approach? Let me write that a little more neatly. So we're finding the limit as x goes to infinity of the y values. And so I went through each of these initial points. X equals 0, y equals 1. That was here. So that was 0, 1. X equals 1, y equals negative 1. Where's that? Oh, that's down here. 1, negative 1. 2 and 1/2. That's here. 2 and 1/2. That's that initial point. 3 and 3/2 is right here. 3 and 3/2. And finally 2, 3. And so at each one of those initial points, the question is, if you hop on a solution trajectory starting at those initial points, where are you going to end up in terms of y values as you drift to the right? And so I pursued each one of those to the right. I followed this solution trajectory to the right, followed these, and it turns out that quite a few of them just ended up drifting towards this stable solution at y is equal to 1. And then there were a couple here. So these drifted towards 1. And then there were a couple here that are forced down to negative infinity and up to positive infinity. So that's why we got those negative infinities and positive infinities for those two initial points. So that wraps up this lecture on slope fields and direction fields. I appreciate you joining me. We'll come back and we'll study some second-order differential equations later on here. You are watching the Differential Equations lecture series here on Educator.com. My name is Will Murray, and I hope you'll stick around and watch some more of these lectures with me. I'm really excited to be working on differential equations with you. In the meantime, thanks for joining me. Bye-bye for now.